Okay, so what we're doing today, again, like I told you earlier, is that we're going to just take a few notes. That's all I want to talk about today. You can see it up here on the board. We're going to talk about three-dimensional. I want to actually walk through, three-dimensional figures, go through some vocab that we talked about yesterday, and then some new stuff today, because we really only talked about the intro stuff yesterday. So we're going to get some new stuff here. So I'll let you get your notes out and whatnot. Okay, so three-dimensional figures. Now, let's talk about the outline that I gave you yesterday. I believe the videos are online, everything's there. Let's turn that on. Okay, so here's our outline that we talked about yesterday. Number one, we did a bunch of definitions yesterday. So one of the definitions we discussed, that was the polyhedron or polyhedra, right? So that was our main topic yesterday. Polyhedron singular, polyhedra is plural. It's a three-dimensional object. Flat surfaces. So we'll go through that definition here in a second. Now there was a bunch of parts to it. We talked about faces or bases, however you want to call it. We'll review that today. That's a big part of today. The next piece that we talked about was edges, where those faces come together and they make a little seam. That's called an edge. It's like where the line segments are. And then where the corners meet, where all those line segments also intersect, that's called the vertice or vertex. Singular is vertex. Still the same words. We've been using those words a lot. The only real new one was faces. We really haven't seen those. Okay? Now, regular polyhedra, that is a three-dimensional object that has every wall is exactly the same dimension. So, for instance, and Mr. Brownson let me borrow this. That is a regular polyhedra, ignoring all the lines and the way that you can manipulate this little this Rubik's item. This was the dodecahedron that we talked about yesterday. I'll put it back on the board. It has 12 sides. They're all perfectly pentagons, and you can see it. This is one that yesterday I showed you was like a top-down view. I called it a princess cut diamond. That's kind of what it looks like. It's got the top, bottom. They're parallel to each other. And then it's got, 5 pentagons going on the top, 5 around, and then the one on top and bottom, so it is 12-sided. But they're all regular. The walls are all exactly the same dimensions, and the angles are all the same as well. Now, the book refers to those as the Platonic Solids. It's the same difference. It's however you want to say it. But there's 5 of them, so we'll review those words one more time in case you didn't get those written down yesterday. That was the last slide that we did. We only did like 2 slides after this one yesterday. We're going to do a lot more today. Now, today's terms, just so you understand like what we're doing today, we have a couple of vocab terms I want to talk about. Number one, we need to talk about the prisms. Okay, what are they? What are the names? How do you know if it's a prism versus a pyramid? Right? What are the difference in definitions? Because both of those shapes are still polyhedra. They're just traditional shapes that you'd think of. Okay? Then we'll talk about the non-polyhedra today, which are cylinders, cones, spheres, three-dimensional objects that are definitely not flat edges. We'll talk about those definitions. That's my goal. I want to get through that stuff today. When we get through that, perfect. Good. Now, if we can, I want to introduce what we're going to do tomorrow. I'm just going to introduce it. Maybe I'll have you just write down the chart. Okay? We're going to talk about volume and surface area, and that'll be our new formulas for tomorrow. We're not going to get an assignment tomorrow. We're going to do an in-class activity, writing a little piece of paper out. You try a problem or two, and then you go about your business. All right. Questions with the outline today? Perfect. Okay. And now again, just like I've said the last couple days, if unfortunately if you get placed in quarantine at some point, this is probably a mathematical probability. We all will at some point. Just make sure check your emails a lot from every teacher. I send out a lot. Sorry, I do. For those who are in quarantine or out, I Zoom every single day, so I expect you to be in Zoom. I post the videos every night. You got the website working, so it is working. You can go back and watch those films. I'm just going to backlog some of the old ones and start putting them on the website, make it look good, and make sure they work, because that's the problem I was having before. Yeah, so this is the tough part. You have to kind of learn it on your own and kind of apply and still do the homework. Submit homework via email and take pictures of it. That's how other students have been doing. Okay, Questions though? Okay, now let's talk about the polyhedron. These are the slide you had yesterday. I'm going to click through this really fast. We talked about the definition of a polyhedron, right? Singular. It's a three-dimensional object. It's a solid. It has faces for walls, so it's got polygons that can come together and enclose a single region of space. So it's got flat surfaces, but they're polygons. But it is a solid. Notice that single region. I don't want like weird cavities in this thing. It's got to close one massive area on the inside as best it can. That's a polyhedron. Okay. Now, this is the ideas that we were talking about yesterday: face, edges, and vertices. Faces are the actual walls. Like on this one, this front face is a trapezoid. The top would be a rectangle. This side might be a rectangle over here, or maybe a parallelogram. However you see it. But again, it's a three-dimensional object that encloses a region. Edges are the walls, the line segments, and then vertexes are those corner pieces. But again, these were the definitions that we talked about right here, those three. Now, on this particular picture, vertices, by definition, it's where all three, segments or more, the three edges come together. So if you look at a pyramid, you could have more than, three actual edges come together to meet at a singularity, a point. It's still called a vertex. It's got to be three or more. So when you look at the top picture, there's three edges coming together to make a vertex, three or more. Now, this picture had a base on it, right? Bases are still faces. It's just the one that's on the bottom. They usually just refer to it as base. Now, if there's two that are parallel to each other, if you have a top and bottom that are exactly parallel to each other and they're kind of the same dimension, they call those both bases. That's kind of the new thing today. That's the part that I really want you to understand. We still call them faces, but the two that are on top and bottom, if they happen to be the exact same picture and they're parallel to each other, we call them bases. That's a massive important thing for later on when we start naming all these polyhedron today. Okay? Questions with the basic terms that we talked about yesterday? Okay. Now we talked about the Platonic solids or regular polyhedra. Okay, this is the definition that was on the last slide, right? It's a polyhedron where all the faces are regular, congruent polygons. They're all the same. They're all equal to each other. And all the edges are equal in length. Now there's 5 types of regulars. We talked about this yesterday. Tetrahedron, 4 equilateral triangles coming together. Okay. I don't know if I have them here for. Actually, I do. I'll walk around and I can show you this. Fortunately, I had somebody come in and let me borrow some of their Dungeons and Dragons die. So I put my little mouse, you can see it. 4 equilateral triangles meeting. Doesn't matter. It works. This is, they made a die out of it, so it doesn't matter what side it lands on. You can see it? Yeah, equilateral, so it has fair chances to land on any particular side. So you can see how it kind of works. We brought that in today. It's got equilateral triangles for all the walls. I thought it was kind of interesting when you start to see how do they make a die out of something like that. The number on the top would be the number you look at. Now, the next shape, that would be the normal hexahedron, the cube. Most people know this one. I don't even probably need to walk around. It's the traditional die that you have with that. If it's a well-balanced die, the pits where the numbers are shaped, they'd be deeper on the one side than the 6 side. The 6 side would be more shallow. That's something that you should recognize when you have a weighted die. The pits would be the same distance, so it won't be actually a fair toss. The one side has to be deeper than the 6 side. Another thing in Las Vegas, they make the dies clear, like see-through green or see-through red. So when you hold your hand, you can see your fingers through it, so they know it's not weighted. It's perfectly plastic. That's something you need to think about when you're playing a game of die. Is it actually weighted? Is it a true die, and will it give you a fair chance? Octahedron, where there's 8 equilateral triangles. This is the shape that I told you yesterday. 8 equilateral triangles. So, yeah, this would be the one. I'm gonna walk around. So it looks like that. It's like basically a square pyramid on the top and bottom, kind of purpley spaced. You can see that. It's got 8 equilateral triangles. Kind of easy to roll. One number to be face up. That's the number you go with. Okay, then we talked about a dodecahedron. That was the next one. That was the one that I showed you here. Mr. Bronson allowed me to borrow his Rubik's item. But there's 12 sides and they're perfect pentagons. They're all exactly the same walls. They're all exactly the same angles in every corner. It is a perfect dodecahedron. I don't even want to mess that up. I don't know if I would ever get it back. And then obviously the last one is a icosahedron 20-sided. I don't know if I have a 20-sided die. I do, in fact. Okay, now I'm going to show you the picture of this. I can't see it from the picture, but holding on to it, now it makes way more sense. Once you see it, there is 20 sides to this thing. And it's a bunch of equilateral triangles put together. All kind of a ball almost. Right. So, kind of see that they're all triangle faces. There's 20 of them. I've never been able to image that in my head. So when I go on tonight and I post pictures of these tonight on the website, I'm actually going to take photos of these as well. I'll make a really nice detailed photo of this. I'll bring out my real big DSLR and take some really nice high quality photos of those things. Okay. Questions on the Platonic solids, the regular polyhedron. Okay, now, the new stuff today, because we haven't talked about these. We need to talk about the types of polyhedron, the different types, okay? So polyhedron, the types. There's prisms and there's pyramids. So let's talk about the definition. A prism, okay, by definition, and I'm going to zoom in a little bit. That's a little small for me. Old, and I need to see that better. Okay. Okay, a prism, by definition for a polyhedron, so if you're going to call the item, something and something prism, okay, it is a polyhedron where the two parallel walls that are considered the bases, whatever shape that is, that's what you call it, okay? So whatever two walls were parallel to each other, that's the name of the prism. So if you go back to that original picture, I had the pentagons top and bottom, that would be a pentagonal prism. Now, how you know that is because all the walls that connect the two parallel would all have to be rectangles. So you can see that. They don't, I haven't even posted the picture yet here. So it is a polyhedron where the two parallel walls that are equal are called bases, and that's how you name it. So let's see if I can show you a picture here. So like on this one, like I showed you, the top and bottom are parallel, right? You can see that, they're going the same direction. That would be called a pentagonal prism. And all the walls that connect those two parallel sides have to be rectangles. They have to be flat walls. So you could have any type of shape you want, as long as you have two things that are parallel to each other and you have rectangles connecting them, okay? We'll go through more pictures. Like the next slide just has a bunch of examples of prisms. So you can just kind of get a glance at some of them. Questions with that? Again, the parallel walls are how you name it, and then the walls that connect those parallel walls have to be rectangles. Now, a pyramid, on the other hand, that is the other type of polyhedron. You can have different types of pyramids. It has a base for a polygon, some type of polygonal base. So it could be a triangle, it could be a square, it could be a pentagon, it could be an octagon for the base. But then the walls that go up to the singularity, the point up in the air that meet at the vertex at the top, those walls that go up to the top have to be triangles. So 3 or more triangular faces that go up to the top and meet at a common vertex. So here it is. So pyramid? A polyhedron that has polygonal base and 3 or more triangle faces that go up in the air that meet at a singularity or a vertex. Now, how you name it? You name it by what the bottom is, the base. So in this picture, what does that base look like to you?
Square.
A square, so you call it a square pyramid. Maybe it looked like a rectangle to you, so you call it a rectangular pyramid. Maybe it looks just like a parallelogram, so a parallelogram pyramid, right? You call it by whatever the shape is. Doesn't roll off the tongue when you call it a parallelogram. Okay, questions with pyramids though. Okay, let me keep zooming out here. Now we're going to look at the next slide has a bunch of examples of these. All right, now those are the polyhedron, right? That's how you name it. They're either prism or a pyramid. That's what you can call it. Okay. Now the non-polyhedron, or conic sections, if you will, pieces of cones or three-dimensional objects, the conics. Those are non-polyhedron because they have curved edges. So like, for example, if we talk about a cylinder has circles that are parallel to each other. Top and bottom are circles that are parallel, and it is a curved rectangle that connects it. A curved surface. So just think about that. If you were to take a pop can, where's my markers at? So I'm going to show you the picture of a cylinder here. So imagine you took a pop can, you cut the top off with like a little can opener, and same with the bottom, you took those off, so those would be 2 perfect circles. And then if you cut down the seam for the actual body of the pop can, and you rolled it out, the body is an actual rectangle. If you think about it, if you just rolled out a pop can. Okay, questions with a cylinder. Curved. Now, if you were to find surface area for that thing, you can see the 3 objects that make it. It's a rectangle, it's a circle, and a circle. Next, a cone. A cone. A cone is a type of, non-polyhedra where it's got a circular base and it's got a curved surface that connects it. And that's the hardest part. If you were to take a cone, and let me show you a picture of it, right? Here's your cone. You can see that it has a circular base, and if you were to cut up the cone, what you'd be left with is kind of an image that it would almost look like this. It's not quite a rectangle, it's kind of like a curved edge to it, where they kind of come together. It's more almost triangular in shape, but almost like a softball outfield or a baseball outfield. So it's not quite rectangular, not like the pop can. Then the last one obviously is the sphere, right? Sphere, by definition, it is all the points equidistant from a central location. Like that, right? Our sun that we orbit is a sphere. The Earth, on the other hand, is not. It seems weird. Earth is not a perfect sphere. It's close. It's off by 50 or 60 miles north and south. Why that is? On the galactic plane that we're on in our little solar system here, the Earth and all the planets are on a disk. Okay? So if you imagine this is the sun, and then we would be very small specks, very, very far away from it. We're just tiny little specks. And you have Mercury and Venus and Earth and Mars. We're all basically in a perfect plane around the sun. The only one that wasn't was Pluto, and they've since have said Pluto is not a planet. They've taken it out back in the early 2000s. They declassified it because it wasn't on the solar plane. It was a weird distance. It didn't have a nice circular kind of orbit. It was more very erratic ellipse or oval type of shape, but it was on a different plane completely. You know, there's been arguments about putting it back, but it doesn't fit the definition of all the other planets. And so there's lots of things that basically, if you looked at that picture I gave you, there's lots of reasons why the Earth is not spherical. Because in the plane that we're in, the gravity of Venus, Mars, Jupiter for sure, is elongating us, plus the sun. We're basically being pulled like taffy.
So eventually we'll be...
Not quite. We've kind of solidified at this point, but we've been pulled more like an elongated football, but not as exaggerated as a football would be. So we're pulled more along the equator than we are along, you know, the North and South Pole. So the North and South Pole have shrunk in a little bit since we formed, and then the equator is a little bit longer. So that's why, like, when you fly in an airplane, okay, when you fly in an airplane, you actually want to fly north and south. So when they fly, like, from, let's say, New York to England, they try to go through the North Pole. They try to go north instead of just east-west that you think they would. Because going east-west, you're like, oh, well, you know, New York and England are almost directly east of each other. But if you fly north, it's a shorter distance. Because it is shorter along the poles. It's about 50 miles or so that it's been shortened. A lot of people don't know that. It's just kind of weird. There's different formulas to figure out, you know, the distance you actually traveled along a path. But yeah, there's just the plane that we're in, it is elongating us a little bit. But yeah, just kind of cool when you start to look at all the different aspects of the, you know, the solar system, look at how they're all affecting each other. Now, let's talk about the actual polyhedron themselves. I've kind of given you the names of, like, all the pyramids, right, and all the cylinders. Well, or not cylinders, but prisms. Let's go through some pictures of them. So let's talk about the prisms themselves. They're based on the bases, right? So if you look at the two walls that are parallel, so if I give you a triangular prism, right, you have the, now this is really hard to see. It looks like a tent to me. Okay, so you have like a little triangular tent where the triangle is the front and back. Do you see that those are parallel to each other? Now, I don't know how you see it. Maybe you see this one coming out at you, or maybe you see this one coming out at you. I don't know how your eyes adjust to it. But the front and back triangles are parallel, so those are your bases. Even though I know it's not sitting on it, but the bases are the two walls that are parallel to each other. And then there's perfect rectangles that connect them. So it is a triangular prism. Right? You could have a rectangular prism, where you have two rectangles that are parallel, and there's all rectangles that connect them. I don't care how you look at it. Top and bottom could be your bases, they're rectangles. It's a rectangular prism, right? It could be a pentagonal prism. Maybe the top and bottom are pentagons, right? So the top and bottom are parallel. So it's a pentagonal prism. Rectangles connect them. Do you see how that works now? Okay, I don't think I need to go through more than that. Now let's talk about the pyramids. Okay, a triangular pyramid. The base has to be a triangle, and then there's triangle faces going up in the air. That was that shape I showed you earlier. This is the same picture I used for the tetrahedron, sorry. But it's a triangle base, and then there's triangles going up in the air, so it is a triangular pyramid, right? You can have a square pyramid or a rectangular pyramid. That's like the pyramid of Giza. I'll show you pictures of that here in a minute. Okay, the bottom is a rectangle, or a square, or whatever you want to call it, and then it would go up in the air with triangles, right? You can have other weird shapes, like a pentagonal pyramid, right, where the bottom's a pentagon, and then the triangles go up in the air. So that's how you name a polyhedron, right? You name it by whatever the base is, and then what are the walls that connect to a singularity. All right, questions with all of those? Now, there's more. I just gave you a bunch of examples out of the textbook. I was pulling pictures right left and center. Okay, we good with those? Okay. All right. Now, let's talk about you know, the actual pyramid. Let's go to the pyramids, I think, first. I think we probably should talk about, you know, the actual square pyramid again, because the pyramid of Giza is not triangular. So if we go back to that picture I showed you a long time ago, you know, the Great Pyramid of Giza, that was a picture I showed you a couple days ago. This is one of the other pyramids. This is in Khufu's temple. This is the smaller one. You can see it's square nature. The walls for the pyramid itself are at perfect 90 degrees from each other. The bases, they face perfectly north, south, east, west. You can see the doorway on this one a little bit better on the smaller one. You can see it's about 15 to 20 yards, or not yards, but feet up in the air. People are significantly bigger on this pyramid. It's still a big pyramid, don't get me wrong, but significantly smaller than the other two. Here's kind of the middle of the pyramids, and then you have the great pyramid of Khufu, the big one, right? Kind of cool. They used to be covered in limestone. We talked about that. Sandstorms kind of blasted it away. So this is actually from a military base in Iraq, I believe, or no, I think this was actually Cairo. I think this was Cairo when they had one come through. You can see it, but the pyramids are so tall that the top's out of the sandstorm. It's hard to see that, but the top is out of the sandstorm, so it wouldn't get weather blasted as hard. Sometimes, yeah, it would be affected, but more or less, that's why the top is still somewhat covered in limestone. You can still kind of see that. All right. The three put together, you can see them there. Yeah, pretty impressive. They've withstood, what was that, 10 to 12,000 years? Question?
Which one was built first?
Which one was built first? Ooh, that is a good question. I don't know. That I don't know. I'm sure there's a way to tell by carbon dating it and looking at it. I don't know. That is a great question. I don't actually know that. You intrigued me there. I don't know. Never really thought about that. Yeah, they would have. I do know it took them about 80 years to build it, to build the big one. I do know that they've kind of estimated 80 years, consistently building with workers. A misnomer about it is, they had slaves. They did have slaves. I'm not going to put that past. But from historical facts. The people that actually worked on it were very proud of the accomplishment that they did. Even though they were still slaves and they went through probably really nightmarish conditions, they're still proud of it. And so that was something that that's I think a reason why they've stood the test of time is they haven't been torn down. Is that that was kind of a huge symbol for Cairo at the time. It was a major mark in their design and their empire at the time, kind of a crown jewel for them. But there's tons of pyramids. Eventually, the Egyptians went away from grand pyramid schemes. They went to step pyramids, isosceles, trapezoid, step pyramids, almost like a layer cake. And then they went to the Valley of the Kings eventually, because they were trying to prevent grave robbing. Because these are just huge, red flags, like I have a bunch of treasure in the inside. So they went to different designs, and it didn't take as much slave power to build a cave inside of a cliffside. So, but yeah, there's still tons of stuff we haven't discovered yet. I love that the archaeology part of it. Now, Great Pyramid of Giza, the inside. This is the size of it, as you can tell. You can see this. I think that's the smaller pyramid. That's the small one, I believe. But look how big it is. It's just massive. Just a massive object. You can see it compared to a plane. The statue of Jesus in Rio de Janeiro. You have the Statue of Liberty and the Eiffel Tower. There's the picture of the inside that we know of. There's still, what I talked about last time is that. Let's see, this is dying. There is a chamber that they can detect by radar that's up here still, and another chamber that's over here, but we can't get to it. We know that there's a doorway on that one left side that they can see it with they used infrared, and they can see that the doorway is a different shade, so it's emanating like heat or cold air through it. So that's how they identified it, that there's another chamber, another doorway. So there's still more in these pyramids that we just can't get to. We don't want to, we don't want to cause damage. That's the new thing with archaeology, is that they want to be non-destructive. Can we look inside the actual, chambers themselves without having to, break down the door? And so they're doing 3D scans and, echo chambers and infrared and trying to see what's beyond doorways. Valley of the Kings, like King Tut's chamber, where they found all, the massive amount of gold that King Tut accrued, in his short tenure of 13 years or whatever it was, or 11, I think it was 11. There's still more chambers that were off of his burial chamber that they haven't opened yet, that they've left because the artwork on the walls were too beautiful, so they left it. And I mean, there could be tons more treasure in there. They just didn't want to be destructive anymore. Because as you can tell, if you looked at photos of any of those archaeological sites, there's too many people around and it just becomes destroyed when people start moving and tearing down things. So, there's the inside the grand chamber. This is a different photo. They installed a staircase in the late 90s, but nowadays you can't even go inside anymore. But that's what it looks like on the inside. The stairwell wouldn't be there normally. But yeah, it's really impressive architecture. And these weren't cut. Like, they weren't cut post-fact. They were built as what we believe is they built it in a spiral and then went to the top, and then as they filled in the bricks, then they worked their way back down from the top and filled in the bricks on the back as they're working down the pyramid and form the structure itself. So almost like you went up a mountain and you had a road going up the outside of the mountain, and then they filled it in as they went back down. And it made the pyramid itself. But just think about this, the architecture that had to be involved in just the engineering, because as you built it going around it, you had to build these chambers that had, were perfectly groomed with bricks that were already placed so that those objects on the inside would be how they're sitting now as you designed it. Very different designing than what we do nowadays with houses, where you put up the outside and then you form the inside later, right, with walls and stuff. They didn't do that. Very different. All right, questions with any of that stuff? Okay, I'm gonna probably stop there today. Just the reason why I want to save the surface area and volume stuff for tomorrow. That's going to be our big thing for tomorrow. Questions with any of the stuff we kind of went through today? Well, there you go. Get rid of this here. Here's your schedule for today.